40 light-years away, nestled within the faint ruby glow of the constellation Aquarius. We discovered not just a planet, but a kingdom. 7 worlds, all roughly the size of our own Earth, huddled in a tight, frantic embrace around a single, diminutive star known as TRAPPIST-1. It was a statistical impossibility rendered into physical reality. Never before had we seen such a concentrated collection of terrestrial worlds. A celestial clockwork so precise and so packed that it challenged our understanding of how solar systems are born. This is the holy grail of exoplanet research, a natural laboratory where the laws of habitability are being tested on a grand scale. Each of these 7 sisters offers a different answer to the same existential riddle. Is the spark of life a common occurrence in the universe, or are we a solitary fluke in an endless, sterile void? Before we begin our journey into the heart of this crimson system, I invite you to support our exploration by liking this video. To understand the 7 sisters, we must first look at the hearth around which they huddle. At the center of this clockwork arrangement lies TRAPPIST-1, a star that defies our common intuition of what a sun should be. If our sun is a roaring golden bonfire, TRAPPIST-1 is a glowing ember, a deep ruby spark in the velvet dark. It is classified as an ultra-cool M-Dwarf, a category of star so small and so dim that it remains invisible to the naked eye. Despite being relatively close in our cosmic neighborhood, to stand on a planet in this system would be to see a sun that is not yellow-white and blinding, but a massive, salmon-colored orb hanging heavy in the sky, providing a warmth that is felt more as infrared heat than as visible light. TRAPPIST-1 is barely larger than the planet Jupiter, yet it possesses 80 times its mass, a dense, compact ball of hydrogen struggling to sustain the nuclear fires of its core. This modesty, however, is the secret to its incredible endurance. While massive stars burn through their fuel in a blaze of glory, and stars like our Sun live for perhaps 10 billion years, TRAPPIST-1 is the ultimate survivor. It sips its hydrogen with such extreme frugality that it will continue to shine for trillions of years. When our Sun has long since expanded into a red giant, charred the Earth to a cinder, and eventually faded into a white dwarf, TRAPPIST-1 will still be there, a steady, crimson lantern in a much older, darker universe. This longevity presents a profound biological opportunity. On a world orbiting such a star, life would have not billions, but trillions of years to evolve, to adapt, and to reach heights of complexity we can scarcely imagine. But there is a trade-off for this immortality. Because the star is so cool, the habitable zone, that precious region where water can remain liquid, is squeezed incredibly tight. To stay warm, these planets must orbit so closely that their years are measured in mere days. They are huddled together in a space smaller than the orbit of Mercury, trapped in a gravitational embrace that is both life-giving and potentially perilous. Here, the laws of celestial mechanics are pushed to their limit. We are looking at a system that operates on a different fundamental rhythm than our own, a testament to the sheer diversity of the cosmic architecture. In the red light of TRAPPIST-1, we see a vision of the universe's distant future, a sanctuary for life that could persist long after the great galaxies have grown cold. If we were to look upon the TRAPPIST-1 system from above, we would witness a spectacle of celestial mechanics, unlike anything in our own solar neighborhood. Here, the 7 planets are not scattered across vast distances, but are woven together in a tight, intricate web of gravity. They move with a synchronization so perfect it borders on the mathematical sublime. This is what astronomers call orbital resonance, a state where the orbital periods of the planets are related by simple whole number ratios. It is a chain of connection that links the innermost world to the outermost, ensuring that they pass one another at regular, predictable intervals, their gravitational tugs acting like the rhythmic beats of a cosmic heart. To understand the scale, imagine our own solar system compressed. All 7 of these worlds orbit their star at a distance much closer than Mercury orbits our Sun. They are packed together like passengers on a crowded train, so close that if you were standing on the surface of one, the neighboring planets would not appear as mere points of light, but as massive, looming spheres in the sky, sometimes appearing larger than our moon looks from Earth. You could watch the clouds of a sister world drift by, or witness the transit of another sibling across the face of the red sun, all within a matter of hours. This arrangement is not just a visual marvel, it is a musical one. When scientists translate the orbital frequencies of the TRAPPIST-1 planets into sound, they discover a complex, haunting melody. The system is essentially a symphony written in the language of gravity. For every 8 orbits of the innermost planet, the next one completes 5. For every 5 of the second, the third completes 3. This 8 to 5 to 3 resonance chain continues through the entire system, creating a stability that has endured for billions of years. In a universe often defined by chaotic collisions and violent upheavals, TRAPPIST-1 stands as a testament to order and harmony. It is as if the laws of physics themselves conspired to create a masterpiece of clockwork precision. But this very beauty raises a haunting question. How can such a fragile, tightly wound system survive the tempestuous nature of its host star? The harmony we hear may be a defiant song played against a backdrop of stellar fury, a delicate balance between the grace of the dance and the violence of the fire. The tranquility of the TRAPPIST-1 system is, perhaps, a mask for a more violent reality. While we marvel at the mathematical elegance of their orbits, we must confront the harsh truth of their environment. Red dwarfs like TRAPPIST-1 are not the steady, predictable beacons that our Sun is. They are temperamental. In their youth, and even into their maturity, they are prone to ferocious stellar flares, titanic eruptions of high-energy X-rays and ultraviolet radiation that dwarf anything our Sun produces today. For planets orbiting so closely, this is not merely a weather event. It is an existential gauntlet. These worlds are bathed in a constant torrent of charged particles, a relentless stellar wind that threatens to strip away the very atmospheres that make life possible. The scientific community is locked in a profound debate over the fate of these 7 sisters. Skeptics argue that the proximity to the star is a death sentence. They suggest that over billions of years, the relentless bombardment has boiled away the water and blasted the protective gases into the void. leaving behind nothing but scorched, airless husks, skeletons of worlds that might have been. Early data from the James Webb Space Telescope has added fuel to this fire. Initial observations of the innermost planets, TRAPPIST-1b and 1c, show little evidence of thick, carbon dioxide-rich atmospheres, suggesting they may be bare rock, as desolate as the Moon or Mercury. Yet, the story is far from settled. Optimists point to the resilience of planetary systems. Perhaps these worlds started with much thicker atmospheres than Earth. Or perhaps they possess strong magnetic fields that act as a cosmic shield against the stellar gale. There is also the possibility of secondary atmospheres, gases belched from the interior of the planets through volcanic activity, replenishing what the star steals away. We find ourselves in a period of intense scrutiny, using the golden mirrors of Webb to peer through the glare of the red sun, searching for the telltale absorption lines of water vapor, methane, or oxygen. Every new data point is a piece of a puzzle that could confirm our deepest fears of cosmic solitude, or validate our boldest hopes for a galaxy teeming with life. We are watching a cosmic crucible where the potential for life is forged in the fire of a star that could be both a giver of heat and a thief of air. The TRAPPIST-1 system is the ultimate test of our theories, a place where the line between a garden and a graveyard is drawn by the invisible hand of stellar radiation. If an atmosphere does cling to these worlds, it must contend with a phenomenon that is almost universal for planets so close to their star: tidal locking. Just as our moon always shows the same face to the Earth, the planets of TRAPPIST-1 are likely held in a gravitational grip so firm that they no longer rotate relative to their sun. One hemisphere is condemned to an eternal searing noon, while the other is lost in a never-ending, frozen midnight. This creates a world of impossible contrasts, where the very concept of a day or a night has no meaning, and the passage of time is marked not by the rising of the sun, but by the slow, rhythmic pulses of the star's internal fire. In such a place, the climate would be a study in extremes. On the day side, the red sun sits motionless at the zenith, a permanent weight in the sky, potentially baking the surface into a cracked and barren wasteland. On the night side, temperatures could drop so low that the very air might freeze and fall as snow, creating vast, silent glaciers of nitrogen or carbon dioxide. But between these two graveyards lies a sliver of possibility, the Terminator zone. This is the thin ribbon of twilight that circles the planet, a region where the sun is forever setting or forever rising. Here, in this permanent gloaming, temperatures could moderate. A perpetual wind, driven by the temperature difference between the hemispheres, might carry heat from the day to the night, creating a narrow, habitable ring where liquid water could flow and life could find a foothold. We might imagine a biosphere adapted to a world that never sleeps. Plants, perhaps, with broad, black leaves designed to soak up every available photon of infrared light, growing in static, shadowed forests. Creatures might evolve with biological rhythms keyed to the flares of the star, rather than the rotation of the planet. It would be a landscape of long, stretching shadows, and a sun that never moves. A world where survival depends on staying within the boundaries of a geographical narrowness. This is life in the margins, a testament to the idea that nature does not require a perfect Earth to thrive, only a persistent source of energy and a place to rest. To look upon such a world is to realize that our own 24-hour cycle is a local quirk, and that across the cosmos, the majority of habitable real estate may look very much like this. A realm of eternal twilight, where the dance of life is performed on a stage that never changes. If we could transport ourselves to the surface of TRAPPIST-1's, a world nestled in the very heart of the habitable zone, we would witness a sky that shatters our earthly concepts of solitude. On Earth, we look up and see a void punctuated by distant, lonely sparks. But in the TRAPPIST system, the cosmos feels intimate. As the crimson sun hangs low on the horizon, we would see the other 6 sisters not as tiny points of light, but as radiant, distinct spheres. We would see them waxing and waning like our moon, their features perhaps visible to the naked eye: shimmering oceans, swirling cloud decks, or the dark basalt of volcanic plains. In this neighborhood, the next Earth is not a lifetime away. It is a neighbor, a stone's throw across a shallow cosmic pond. This proximity forces a profound shift in our philosophical perspective. For most of human history, we have viewed ourselves as an island of life in a vast, indifferent ocean. We have struggled with the great silence, the haunting possibility that we are a singular accident of chemistry. But the TRAPPIST-1's system suggests a different architecture for the universe. It whispers of a great community. A reality where worlds are born in clusters, where the spark of life, if it exists on one, could easily leap to another through the exchange of meteorites, a process known as lithopanspermia. In such a system, the evolution of intelligence would not be a lonely struggle, but a shared journey among siblings. What does this tell us about the commonality of worlds? It suggests that our own solar system, with its vast empty gaps between planets, might be the exception rather than the rule. Perhaps the universe prefers these tight-knit families, these crowded nurseries, where the potential for life is multiplied sevenfold. Looking out from the Terminator of TRAPPIST-1's, seeing those other worlds hanging in the salmon-colored sky, we are forced to confront the idea that we are not the center of the story. We are merely one expression of a cosmic law that delights in variety and abundance. The TRAPPIST paradox is that in its very strangeness, it makes us feel less alone. It reminds us that the ingredients for our existence, rock, water, and starlight, are being combined in countless ways across the dark, and that the solitude we feel on Earth may simply be a matter of distance, not of destiny. We are part of a legacy of worlds, a grand experiment in planetary architecture that is only just beginning to reveal its secrets. We are living in the dawn of a new enlightenment, a pivotal moment in the human story where the abstract becomes tangible. For years, the TRAPPIST-1 system was a collection of mathematical probabilities, a set of shadows detected by the rhythmic dimming of a distant ruby spark. But the arrival of the James Webb Space Telescope has fundamentally altered our relationship with these 7 sisters. With its massive, gold-plated mirrors acting as a sentinel at the edge of the void, Webb is capable of peering into the very heart of the infrared spectrum, catching the faint, ancient photons that have traveled 40 light-years to reach us. It does not merely look at these planets. It begins to breathe their air, parsing the light that filters through their upper atmospheres to reveal the chemical fingerprints of other worlds. The Webb era has brought us to the threshold of the unimaginable. Through the precision of transmission spectroscopy, we are now engaged in the painstaking process of searching for the signatures of life. The presence of carbon dioxide, the signature of methane, and the elusive, shimmering promise of water vapor. Initial observations of the innermost worlds, TRAPPIST-1b and 1c, have provided a sobering reminder of the challenges of the M-Dwarf environment. These inner planets appear to be stark, airless rocks, stripped of their primary atmospheres by the early fury of their host star. Yet these were always the scouts, the worlds most exposed to the stellar wind. Our gaze is now shifting outward to the trio of planets nestled in the habitable zone, D, E, and F. These are the true prizes of the system, the worlds where the climate may be stable enough to support the liquid oceans that are the cradle of all we know as life. As we sift through the data streaming back from the Lagrange point, we find ourselves in that breathless silence before a great unveiling. We are like the early cartographers standing on the edge of an unknown continent, waiting for the fog to lift. Whether we find a series of lush, clouded biospheres or a collection of silent, icy deserts, the outcome is secondary to the act of the search itself. To look for life elsewhere is to affirm the value of our own existence. It is a testament to a species that, though fragile and tethered to a single blue marble, has the audacity to reach across the light years to touch the face of the infinite. The TRAPPIST-1 paradox is the ultimate mirror. It reflects our curiosity, our technological prowess, and our undying hope that the universe is not just a collection of matter and energy, but a house of many mansions. We are the cosmos observing itself, a brief, flickering consciousness mapping the dark. And as the red sun of TRAPPIST-1 continues to glow for trillions of years, our search for its secrets will remain a defining chapter in the legacy of humanity, a journey from the solitude of our birth to the potential community of the stars.